So when we're given a covalent compound, we can draw its Lewis structure. And then after we have its Lewis structure drawn, we can predict what is the three-dimensional shape of that molecule going to be. Because when we draw the it's 2 dimensions, it's flat. And so it doesn't totally always show us like what does this really look like in real life if we were to actually see the molecule in 3 dimensions. And so we have this thing and it's called VSEPR, and I'm going to talk about what it means if you haven't already seen it on Canvas. But it's a theory that allows us to use the number of bonds and the number of lone pairs of electrons that are around a central atom in a molecule in order to predict the shape. Because if we can draw the Lewis structure and then we can identify how many bonds and how many lone pairs does it have around the central atom, they're all going to follow that pattern of that shape if they have that many bonds and a certain number of bonds and or lone pairs on the central atom. And so if you can identify how many bonds and how many lone pairs are around the central atom, then it's really easy to predict the shape because they're all going to follow that pattern that you're going to see in your notes today. So I'm going to switch over and share my screen so we can look at Canvas for a little bit, and then I'll turn it back off because I'm going to show you guys some actual molecules a little bit later. So again, this is what we're doing today. You're going to be able to deduce the three-dimensional shape and the bond angle of molecules from their Lewis structure. So if you are shown, excuse me, if you are shown a Lewis structure of a covalent compound, you should be able to look at it and you should be able to count, look at the central atom and count how many things are bonded, how many lone pairs does it have around it. And from that information, you should be able to deduce. That means you should be able to tell me what shape it is because there's different names of shapes that you're learning about today. And then you should also be able to kind of identify what's called the bond angle. And that's just, you know, like in geometry, we measure the angle between two lines. Well, you can measure this. The lines, in this case, there are bonds. And so it's the angle between two bonds in a molecule. So in your lesson on here today, it starts out with just a recap of covalent bonding from Monday. And it's just reminding you that covalent bonds happen when you have two nonmetals that are sharing a pair of electrons. So ionic bonds, there was a transfer. The metal gave its electron away and the nonmetal took it. And then you had your positive and negative ions that formed a bond between the positive and negative charges. In covalent, they're sharing nonmetals. They're both nonmetals, but they're sharing the pair of valence electrons. So that's how they form that bond and create a molecule. And so anytime we have a shared pair, we call that a bonding pair. And when we draw the Lewis structures, like what we did on Monday, we represent a line or a dash connecting the two element symbols to indicate, hey, these two atoms are sharing a pair of electrons in this bond line, okay? And then remember that in covalent bonds, we can actually have what we call multiple bonds. So a double or a triple bond, meaning that they're going to be sharing more than one pair of electrons. And so every pair of electrons is a bond line. And so down here, it has kind of a visual example. And so here are the two atoms. We've only drawn the valence electrons. We haven't included the inner electrons because the valence electrons are what we care about for bonding. And so this one, here is the chemical formula. It's Cl2. So that tells me that it's just two chlorine atoms that are bonded to each other. And so what happens is chlorine on the periodic table is in group 17, which means it has 7 valence electrons. And that means that each one of these has one single one. So they each have 3 pairs because they have the 6, and then their last one is single. That's the 7th one. So that single one on each one, those are going to pair up together so that they can create that covalent bond. So these two atoms are sharing this one pair of electrons here. They each donated one, and they're sharing that pair in between them, and that creates the covalent bond. So when we draw the Lewis structure, it looks like this, and here's the one single bond line that's connecting these two chlorine atoms, okay? And it's making a molecule of chlorine gas. The same thing here. This one, though, it's O2. This is an oxygen molecule. So this is the naturally occurring oxygen that we breathe. This is what it is. It's O2. It's not a single oxygen atom. It's 2 oxygen atoms that are covalently bonded. And in oxygen's case, because oxygen is in group 16, that means it has 6 valence electrons. And so what happens is in order to satisfy their octet, they actually, both of the single ones on each oxygen are going to pair up with the two singles on the other oxygen. So you end up with them sharing 2 pairs or 4 total electrons between them to satisfy both of their octet rules, okay? And so here, when we draw the Lewis structure, we have 2 bond lines because it's representing a double bond, because there are 4 electrons or 2 pairs of electrons being shared here instead of just 1 pair like on chlorine. Nitrogen over here, this is nitrogen gas, the nitrogen molecule. Just like oxygen and chlorine, it doesn't occur in single atoms. Naturally, nitrogen gas is already paired up in a molecule like this. So it's N2, and so kind of the same thing. They're going to share, but in this case, nitrogen's in group 15, and everything in group 15, they have 5 valence electrons. They have 1 pair, and they have 3 singles. And so what happens if 2 nitrogen atoms are going to bond is they actually share 3 pairs. They share 6 electrons because they had 3 singles, and so each single is going to pair up with one of the singles on the other nitrogen. And since it's sharing 3 pairs or 6 total electrons, that creates a triple bond. And so for nitrogen, we have the 2 ends and we have 3 lines between them to indicate that it's a triple bond and 3 pairs of electrons are being shared. Okay. So that's going to be important for today because we have to be able to count, you know, how many bonds does something have? How many lone pairs does it have? Because our topic today, it's called VSEPR is kind of the nickname for it. It's the acronym, but it stands for valence shell electron pair repulsion. And what VSEPR is it's a theory. And in science, a theory is something that's been backed up by data. Okay. And so they have looked at several different molecules. They've measured things. They've tested things. And all of the evidence has pointed to this being correct. So it's a theory. And what it does is it helps to explain why covalent molecules have the 3-dimensional shapes that they do. And the reason is because of the number of bonding and non-bonding electron pairs that are on the central atom. So again, it goes back to being able to draw the Lewis structure. And then once you have the Lewis structure, all you have to do is find the central atom and count how many atoms is it bonded to and how many lone pairs does it have on it. And then you simply look up that information and see which shape that's going to match to. So down here, here is the Lewis structure. So this is the chemical formula. It's NH3. So we have 1 nitrogen and 3 hydrogens. And I told you guys last time, hydrogen will never be the central atom because it can only make 1 bond. So nitrogen is going to be the central atom because it has 3 single electrons. It can make up to 3 bonds. So nitrogen goes in the center, and then we bond each hydrogen to it. They're bonded with a single bond because they're sharing a pair of electrons. And then nitrogen also still has this lone pair on it. It had this at the beginning because remember, it started out with 5. It started out with a pair and 3 singles, and the 3 singles are what shared and paired up with these hydrogens. So when we look at the Lewis structure, and this is actually called ammonia. So this is actually what's in like Windex and certain glass cleaners. Ammonia is what this substance is called. But the Lewis structure for it, it's drawn like this. And so I can look at this structure and I should be able to look at that nitrogen that is the central atom and say, okay, there's 3 bonding pairs of electrons because there are 3 atoms bonded to it. There's a hydrogen here, a hydrogen here, and a hydrogen here. That's 3 bonds. And then it also has 1 non-bonding pair, and we call that a lone pair of electrons. And it's here on the central atom, which is the nitrogen. The reason that's important is because if there's a lone pair, that's going to affect the shape. If there's a lone pair on the central atom, it's going to affect the shape. And so even though we draw it on paper like this, this is not what it looks like. If we were to actually build a 3D model of it, it looks like this over here. The lines are not straight out to the sides and straight down to the bottom. They're all 3 actually kind of angled downward slightly. And so it actually kind of makes like a pyramid shape when you look at it. And so they're all angled downly because of the R in VSEPR, the repulsion. So repulsion means that you're repelling or you're pushing against something. And so the VSEPR theory says that because all of the things holding the bonds together, those are all pairs of electrons. And what charge do electrons have, guys? Who remembers this? Do what? Yes, so electrons are negatively charged. So if there's a pair of electrons, you know, here in this bond, and there's another pair of electrons in this bond, they're both negatively charged. So they're going to naturally repel and push away from each other. But the catch is that it can't break this molecule. It can't break its own bonds. And so what happens is that the bonds, all the electron pairs that are in the bonds holding our molecule together, they are repelling or pushing against all of the other electron pairs in the other bonds that are in the molecule. And so they want to be as far away from each other as possible, but the catch is they can't break the bond of the molecule. And so what happens is that's what causes our different shapes, because if I have more or less bonds or more or less bonds with lone pairs, all the shape is going to change, because the more bonds I add, the angles are going to get smaller and smaller because they can't get further away from each other. And then, like I said, if you do have a lone pair, that affects your shape. So this lone pair is actually repelling more. So anytime you have a lone pair, it affects the shape because it repels the bonds more than if it was just another bond up there. And the reason for that is because if you think about it, these electron pairs that are all in these bonds, like these three here that are connecting the nitrogen to each hydrogen, they're sort of like multitasking, if you kind of think of it that way. They're repelling against each other, right? Because they're all negative, but they're also using a lot of their energy to hold this bond together. They're holding this nitrogen and hydrogen atom together. And so because of that, it's kind of like they're distracted and they're not repelling as much as they could if they were focused only on repelling. So it's kind of like, if you think about if you've ever tried to multitask and try to do like 2 or 3 things at once, sometimes one of those things doesn't get done as well. And that's kind of what's going on here. The ones in the bond, yes, they're repelling, but not as well as this lone pair, because this lone pair, it's just sitting up here being negative. It's not connecting to any other atoms. It's not holding 2 atoms together in a bond and using some of its energy for that. It's just sitting up here. That's like its only job. It's like that person that's always negative to you, no matter what happens. Okay, you can't ever cheer them up. So they're repelling these 3 bonds and pushing them further. So that's why they're all 3 angled downward, and they're not kind of just straight to the sides and pointing down like we see in the Lewis structure. Okay. And so when you're looking at your Lewis structures, just remember that just because the Lewis structure is drawn a certain way does not mean that's what it looks like in 3D. To know the 3D shape, you have to look at the number of bonds and lone pairs and then figure out the name of the shape and what it would look like based on that information. So the bulk of your lesson today is actually on this third part, and it's in a video, okay? So if you have not gotten to this yet, then you need to get to it, because this is essentially the lesson today. It's in this video. And he goes through and he talks about the different types of atom or molecules that you could have. He starts with ones where there are 2 things bonded or 2 things around the central atom. Then he goes up to 3 things, and then he goes up to 4 things, because remember, our octet, you can have up to 4 bonds or 4 things around the central atom, because you want 8 electrons or 4 pairs. And so as you watch this, it's going to stop and it's going to ask you questions to make sure that you're understanding and paying attention and all that kind of stuff. And then it's also going to pause and it's going to tell you, hey, make sure you wrote down this information about this shape, okay? Because you want to make sure that you write down like the name of the shape. You want to make sure you write down what that means. So, if it's linear, then that means it has 2 things that are around the atom, the central atom. So you want to write down the name of it. You want to write down how many bonds and lone pairs it has around it, how many things total, and then how many of them are bonds, how many of them are lone pairs. And then you want to make sure you maybe write down the example. So he's going to give you at least one, sometimes more than one Lewis structure example for something that would fall into that shape category. And then he's also going to show you these 3D models. And so you might want to try to draw in like to your best ability. Obviously, drawing on paper is not the same as 3D, but you can still try to represent it on paper, what it kind of looks like. And then you also want to include the bond angle. He'll also tell you the bond angle for each of the molecules. So you want to make sure that you have that information down so that you can refer to it when you're doing your practice, and also next week, because on Tuesday next week, we're going to be taking our unit test, and this is the last thing that's going to be on there. And so you want to make sure that you have that written down so that you can refer to it when you're working on stuff. The next 2 pages, so this one's called Vesper Introduction. The next 2 pages are videos, but they're advanced, okay? So if you haven't gotten to these yet today, that's fine. You can watch them later. But essentially, these two videos have to do with what we call molecules that defy the octet rule. So our octet rule says that everything can only have 8 valence electrons, right? So that means everything can only make 4 bonds because they can share 4 pairs or 8 electrons. Well, we lied. There are some elements as you go further down the table that can actually have more than 8 valence electrons. And in fact, they like having more than 8 because that actually makes them a little bit more stable. It's when you start getting into the elements that are down further down that have the D block electrons in them, because things start always getting weird when you add the D block electrons in, okay? So these are going to be things like sulfur, selenium, a lot of our halogens like chlorine, bromine, and iodine that are further down can do this. And even one of our noble gases, even though we talked about noble gases don't really make bonds, well, guess what? The ones down at the end of the table can, because xenon is actually one of these ones that defies the octet rule. And so it's the same premise. You're still looking at the number of bonds and the number of lone pairs to determine the shape. It's just that you're going to see some that they're going to have more than 4 things on the central atom, so they're going to have more than an octet. So this video focuses on things that have 5 things around the central atom, so they're going to have 10 valence electrons or 5 pairs. And then the is on things that have 6 or molecules that have 6 things around the central atom. And so they're going to have 12 valence electrons. It does not go higher than that, okay? But you do need to make sure that you've at least watched these. Even if you didn't get to them before class day, you can watch them later and add them into your notes, because again, it's going to pause and tell you, hey, make sure you've written down all the information and examples and drawn out the stuff for, you know, all the examples for this shape, okay? I'm going to skip here to the end, because the end, it has kind of a nice little summary here for us. And so if we look at this, it says, you know, VSEPR and the shapes of molecules, a summary of the molecule shapes predicted by valence shell electron pair repulsion theory. Now, the stuff over here, I mean, that's nice, but really the information's here on your little graphic, your visuals here. So this is another example of, this is an infographic. So, you know, your project that you guys had last 6 weeks that some of you guys did really well on, and some of y'all, I was kind of like, did we pay attention to the fact that it was supposed to be on 1 page? Because some of us didn't follow the instructions. But this is an infographic that's telling us about VSEPR and the shapes of molecules. So up here, there's a key. So in the key, in the middle of the circle, it's telling you this is what the shape looks like visually. So here's the model for it. Up at the top curve, it says the name of shape and the bond angle. So for example, this one in pink, it says the name of the shape is called linear and the bond angle is 180 degrees. Down underneath the bottom curve, it tells bonding pairs and how many lone pairs of electrons are on the central atom. So you can actually draw this into your notes, or if you can, you know, you can set it up however you want to, but having a chart similar to this where it's all organized is very helpful, because I can say, okay, well, if there's 2 electron pairs and they are both bonding pairs, because it says 2BP, that's bonding pairs, then this is what it looks like. It's a straight line. So the shape is called linear. And the angle between these 2 bonds, because it's a straight line, it's 180 degrees, because that is the farthest apart that those 2 bonds can get from each other without breaking this molecule apart. Then you go up here. Now there's 3 electron pairs around the central atom. Now there's 2 different possibilities here, because they could all 3 be atoms like this one, or 2 of them could be bonds to atoms and 1 could be a lone pair of electrons. And he goes through both of these in the video, and he gives you examples and explains to you kind of about the angles and everything. So this one is called trigonal planar because it looks like a flat triangle. Like if I were to connect these 3 outer, the kind of teal colored atoms, if I were to connect them, it makes an equilateral triangle. And so they're all kind of the same. And the bond angle, because it's an equilateral triangle, the bond angle between all 3 of these angles or bonds is 120 degrees. When I go to bent, what happens is I kind of take one of the bonds is replaced with a lone pair. And so now there are still 3 electron pairs around the central atom. It's just that only 2 of them are bonds. The third one is now a lone pair. So if we look down here, what changed is that this says 2 BP and 1 LP. That's bonding pair and lone pair. So the shape looks like this. And the name of this one, it's called bent, because it looks like somebody took something that was in a straight line, like this linear, and they just put some pressure on it and they bent it in half. And so on the bond angle, when you watch the video, he's going to tell you that the bond angle, really, there's no way to know for sure unless we know the specific elements that are involved in the bonds. So a lot of times on like these where they have lone pairs, we just say they're less than some angle. So since the trigonal planar was 120, this bent with the 3 electron pairs, we would say that it's less than 120 degrees. Because we don't know exactly how much less unless we know the actual elements that are in the bond. So in general, we just say less than 120. Okay. Now, here is where I have 4 electron pairs. So I can have all 4 of them be bonds. I can have 3 of them be bonds and 1 be a lone pair, or I can have 2 of them be bonds and 2 of them lone pairs. Okay. And so on this one, if I start kind of with the one that's got all 4 bonds, look here, it says 4 bonding pairs. This is called tetrahedral, because if I were, again, kind of like the one up here, that this is a flat triangle. I told you we connected them. It would look like an equilateral triangle. If I were to like connect and shade all of this in, it would look like a tetrahedron. It would look like something that has 4 faces, 4 sides. So this is going into a lot of kind of geometry. So those of you guys that are in geometry or have taken geometry, if you didn't like geometry, I'm sorry, you might be having like PTSD flashbacks right now, because this is dealing with things like angles and shapes and all that kind of stuff. This one right here, what's happened is now one of the bonding pairs is gone. One of the bonds has been taken away. It's been replaced by 1 lone pair. So it's still we have a total of 4. It's just 3 of them are bonds. 1 of them is a lone pair. And so this shape, it's called trigonal pyramidal. And the reason it's called that is because if I look, because the bonds are all angled downward, it creates like a pyramid shape, because the central atom is kind of at the top of the pyramid. And then these 3 here, they're all kind of like at the corners of the base of the pyramid. And it's a pyramid that only has 3 sides, because there's only 3 atoms here to connect. And so that's why it's trigonal pyramidal, because later on down here we have square pyramidal, where there are 4 atoms. And so it's a pyramid with 4 sides. Okay. And so this trigonal pyramidal, that's what the NH3 that was on the second slide we looked at, this is the shape it has, because it's got 3 bonds and 1 lone pair. Okay. Then I can take another bond away and make it a lone pair. So now there are 2 bonds and 2 lone pairs. So it's still a total of 4, but now it's 2 bonds, 2 lone pairs on that central atom. This one, it's similar to this one up here where we only had 3 things around the central atom. It's also called bent. Okay. If I were to rotate this, it would actually look really similar to this one up here. The only difference is this one has 4 electron pairs. This one has 3. So this one has 2 bonds and 1 lone pair. This one has 2 bonds and 2 lone pairs. So if you look, the angles are different as well. This one, we just said it was less than 120. This one, actually both of these, trigonal pyramidal and bent, they're both going to just say less than 109.5, because tetrahedral was 109.5. So each of them is going to be a little bit less than that as we add more lone pairs. So these last 2, it starts getting into those ones that defy the octet rule. So here is where we have 5 electron pairs. Here's where we have 6 electron pairs. And kind of the same thing. We start off, here's 5 bonds. I can have 4 bonds and 1 lone pair, 3 bonds and 2 lone pairs, and then 2 bonds and 3 lone pairs. Okay, so there's 4 possibilities here. And then when we get up to 6, there's 5 possibilities, but in the last video, he only goes through these first 3. And the reason for that, and he kind of explains it a little bit, is that these last 2 on where you have 6 electron pairs, these are not really common, like, at all. I mean, is it possible they could exist? Yes, but you don't hardly ever see them. But you do see these first 3 in certain molecules. And so that's why he only goes through these first 3. So the first one's octahedral. Then we have square pyramidal and square planar, because this one's a flat square, just like trigonal planar was a flat triangle. If I connect all 4 of these outer atoms, it's going to make a square. Up here, the ones that have 5, this one's called trigonal bipyramidal. And again, if you kind of think about the names, trigonal means like triangular, and pyramid means a pyramid shape, and bi means 2. So when you look at this one in 3D, it's like somebody took 2 triangular pyramids and they put them together so that their bases were touching. So there's a top of a pyramid here, there's a top of a pyramid down here, and their bases are touching here in the middle. This one is actually my favorite one. In the video, he tells you it's actually, there's different people call it different names. They have sawhorse here on this poster, but in the video, he calls it seesaw. And the reason he is seesaw is because one of the bonds has been removed. It's a lone pair. And so if you actually turn it on its side and make these right here, like the legs that are like staying, on the ground, then this here, these three in the straight line, this is your seesaw, and it can go like up and down and up and down. And so it looks like a seesaw, and so that's why it's called that. If I take another one away, then I get a T-shaped molecule because there's 2 lone pairs and then 3 bonding pairs here. So if you look at it kind of from the side, it's a T. It's just sideways in this picture. And then again, if I take another bond away, I'm left with these 3 that are in a straight line. So this is linear with the 3 electron pairs. Okay. So what I'm going to do now, because you do have practice on here where it's on the next page. I'm going to click and see if it'll load or not. But essentially your practice is matching, because I told you, you're going to have to be able to determine what shape something is from its Lewis structure. So you have some where it's descriptions about like, how many bonds or lone pairs does something have, or what's the bond angle of its bonds. And then you have like some pictures of the 3D models. So like which 3D model would match which shape. But then you also have some Lewis structures that you have to categorize correctly. So these are like these models. So I want to point out that the lone pairs, they kind of look like these purple balloons. A lot of times they'll use this kind of look for the lone pairs because they're trying to tell you that they take up some space. And so this, if it has one of these purple balloons with the 2 dots, that's your lone pair of electrons on the models. Okay. And then you also have Lewis structure. So remember, I told you the Lewis structure, sometimes they fool you. They're not going to look like the 3D shape because we're drawing them flat on paper. So make sure that you look at the central atom and you count how many atoms is it bonded to and how many lone pairs does it have on it. And then that's your information that you use to figure out which category it goes into. Now, this only goes up to the four things. I did not put the expanded ones on here with 5 and 6. So this only goes up to this is only over the first video, okay? That only goes through up to 4 things around the central atom. And you do have up to 3 attempts to do it. So if you do it and you're like, I didn't do very well, you might go back and review your information and then attempt it again if you had trouble with it. So what I'm going to do now, we're going to do some practice to see if we can identify some molecules. So I'm going to hold up. Okay, yep. Okay, I'm done sharing screen. Okay, I'm going to hold up a molecule and we're going to see if you guys can tell me what shape it is. So think about what you need to think about is find the central atom. How many atoms are bonded to the central atom, and does it have any lone pairs? If so, how many? Because those 2 numbers, the number of bonds and the number of lone pairs, those 2 numbers are going to be what will help you to figure out what shape it is. So, how many atoms do I see bonded to the central atom on this one? I got 1, I got 2, and I got 3. Okay, so there are three bonds, 3 bonding pairs of electrons, right? Okay. Are there any lone pairs on this one? I don't see any. Okay, it'll be obvious if there are some. Okay, so 3 bonds and 0 lone pairs. So knowing that information, which of the shape categories would this one be? So we got something in the chat. Anybody else? What do y'all think online? What do we think here in person? Yeah, so it is the one, it's pronounced trigonal planar. Trigonal planar. So when you watch the video, he pronounces all of them. So you can practice pronouncing them. But it's trigonal planar. And because this is the one that I told you, if I kind of connected them, it would look like a flat triangle. So trigonal meaning triangle, and planar meaning it's flat. Because in geometry, remember, if something's in a plane, that means they're all on the same flat surface, right? So if I kind of hold it at this angle, you can kind of see that they're all kind of in the same flat surface. Okay, if I turn it this way, we can see all of them. But if I turn it this sideways, they're all in the same plane. They're in the same flat area, okay? So this one would be trigonal planar because 3 bonds, no lone pairs on that central atom. All right, what about this one? Kind of turn it so you can see all the different areas. So first off, where's the central atom here? Which color is it? Okay, the black one is the central atom. So how many atoms are bonded to it? Let's see. Somebody from home. Victor, can you tell us how many atoms are bonded to this one in the center? You can type in the chat if you don't want to unmute. No, we get silence. Daisy, how about you? Can you tell us how many atoms are bonded to this one in the center? I think everybody at home is not here.
Is it? Wait, with the black one, right?
So this is the center one. So I'm asking you how many atoms are bonded to this one?
4. No, wait, not 4.
If I look up here, here's 1.
And
down
then
here.
2.
2, and then what about this one?
That's 2.
Nope. This is 1 atom. There's only 1 red atom here. Now it's a double bond, but it's only 1 atom being connected. So there are 3 atoms connected or bonded to this central atom. So the reason I brought this one up is because guess what? It's the same shape as the other one we just looked at. Okay, the only difference is this is a double bond, but that doesn't change the shape. In the video, he talks about the fact that multiple bonds, they don't change the shape. So this is still 3 atoms or 3 things bonded or connected to that central atom. So be careful if you have double or triple bonds, because sometimes we forget that and they confuse us and we want to go, oh, there's 4 bonds because this one has 2 singles and a double, but this is still just 3 atoms bonded to the center one. So it's still trigonal planar. It's still the same shape as this one. Yes. So when you draw it, yeah. So if I were to draw this one here, let me see if I can draw it really quick. Oh. I could connect my iPad, but that would not be as fast. So this is what the Lewis structure for that one would look like. There's a carbon in the middle. It's single bonded to 2 hydrogens, and it's double bonded to the oxygen. And I kind of left them off. The oxygen, it has lone pairs on it, but that doesn't change the shape. Only lone pairs only change the shape if they're on the central atom. So this is the Lewis structure for this. It's pointing this way. So you can see that my Lewis structure, I drew the hydrogen straight up and down, but in reality, they're like this because it's trigonal planar. So yeah, even though there's a double bond here, so there's a double bond between the carbon and the oxygen, like I drew right here, that's still just 1 atom being connected or bonded. So it's got the same shape as this one that had all single bonds, because it's still just 3 atoms being connected to the central one. Okay. All right. What happens if I do this? What happens if I have something like this? So where's my central atom here? Red, white, or blue? Oh, I just noticed this is like a patriotic molecule. It's blue. So I don't think of them that way, because so in these models, red is always oxygen, white is always hydrogen, blue is nitrogen, black is carbon. Okay, and then other colors are other elements, but those are the most common ones. So the blue is the central atom. So on the central atom, how many atoms do I see bonded to it? I see 3 atoms. Are you sure? I see 2 atoms.
1.
I see a hydrogen here. I see a hydrogen here that's single bonded, and I see an oxygen here that's double bonded. That's 2 atoms, right? But what's this up here? What do you think this is? It's not an atom. What do you think it is? It's a lone pair. Okay, I could just leave it off. I could just do it like this, but visually, I want to have something there that tells me, hey, look, there's another place here for electrons to be. So in our little models, just like your picture in your assignment, they use these kind of like balloon-looking things because they're representing the fact that there's some space up here where there's a pair of electrons sitting. So this one, this is my central atom, the blue one. It has 2 atoms bonded to it and 1 lone pair. So total, how many pairs of electrons are around it? I got 1, 2, 3, right? But 2 of them are bonds. 1 of them is a lone pair. Okay, so I need to look for what shape has 2 bonds and 1 lone pair. And what's that called? So it's similar to the trigonal planar. All I did was I replaced one of the bonds with a lone pair. It's still got 3 things around the central atom. It's just 2 bonds and 1 lone pair. It is not pyramid something. This one is just bent because it looks like these 3 atoms maybe were like originally in a straight line and I just kind of bent it because this lone pair up here is repelling these bonds and it's pushing them away from it. So anytime I have 2 bonds and 1 lone pair, or I could have this. I could have 2 bonds and 2 lone pairs. Both of these are bent. The only difference is this one's got 3 things around the central atom. This one's got 4. Okay, 2 bonds, 1 lone pair, 2 bonds, 2 lone pairs. Anybody want to guess what this is? So I told you earlier, what's the red color? Anybody remember what I said? What atom that was? Or what element? Red is oxygen. White is hydrogen. So what is this molecule? How many hydrogens are there in here? H2O. So what is this? This is water. This is what water's molecule looks like. Now, a lot of times, like I said, you won't see it with these little things on it. Usually it just looks like this. Okay, but for today, since we're focused on VSEPR, I put the lone pairs on it. So we can see the reason that it's bent is because it has these 2 lone pairs up here on top that are pushing these bonds away and bending them. So this right here, water being bent and having these pairs of electrons up here, this is what makes like the molecular structure of water, this shape, this is what gives water all of its unique properties and makes it so useful. This is why it stays a liquid over long periods or a lot of temperatures. It takes a really high temperature to boil it and turn it to a gas. Whereas other covalent compounds, they turn to gases really easily. Most covalent compounds are going to be gases like carbon dioxide, oxygen gas, hydrogen gas, nitrogen gas. They're all covalent compounds. Water, though, it's a liquid at most temperatures, and it's because of its shape. Its shape gives it something called polarity, which holds its molecules closer together in the liquid form. It also allows it to dissolve a lot of things. So that's why we use water to like make all of our drinks, because it can dissolve and mix with so many other things. And it all relates back to the fact that it has this bent shape. Okay. Let's see. Let's switch this one out. All right, what do we think this one is? So remember, look at this, find the central atom and look how many bonds are on it, how many atoms is it bonded to, and how many lone pairs does it have? So how many atoms are bonded to the central on this one? 4, right? 1, so I can see 1, 2, 3, 4. And are there any lone pairs on it? No, so 4 bonds, no lone pairs. Anybody remember what this one's called? 4 bonds, no lone pairs. It is called, it's tetrahedral. Tetrahedral. Now, if I take away one of these bonds, and I replace it with a lone pair, now this is trigonal pyramidal. Okay. If I take away another bond and replace it with a lone pair, that's when I get this bent like water. Okay. The last thing I want to point out before we go, linears. Linear have a lot of different options. Okay. If they're in a straight line, it's linear. Like this, it's got 2 double bonds, but look, they're all in a straight line. It's linear. This is carbon dioxide. Okay. This is HCN. Okay. It's got a triple bond and a single bond, but it's still linear because there are 2 atoms connected to this one in the center. All of these, this is oxygen gas. It's double bonded, O2. Hydrogen gas, single bonded, H2. Nitrogen gas, triple bonded, N2. All of these, they're all linear because look, they're just 2 atoms connected to each other. So even though this is technically not on that VSEPR chart in the lesson, yes, if you have 2 atoms connected, there's not technically a central atom because to have something in the center, you got to have at least 3 things like this. So anything that only has 2 atoms bonded, automatically that's linear because they're just connected in a straight line. Doesn't matter if it's single, double, or triple, like all of these. Okay. So that's it for today. If you're behind on lesson stuff, you need to get caught up, guys, because we're having our test over Unit 3 next week on Tuesday. So you've already had ionic, metallic, and covalent bonding assignments. Today you have the VSEPR. On Friday, we're going to be reviewing a little bit of everything, practicing more with drawing the structures and identifying their shapes and all the ionic covalent stuff so that we're ready for our test next week on Tuesday. All right. If you guys don't have questions, y'all can sign out because we got like less than a minute to the bell for lunch. Oh, there it is.
Bye. Have a good day.
Bye, guys. Have a good day. Just bring it back here and I'll wipe it down and plug it in to charge. Let me download. Come on, work faster. I thought I stopped recording. It won't stop recording. There we go.